So let's begin talking about linear inequalities in one variable. Solving linear inequalities is similar to solving linear equations. So if you recall how to solve a linear equation is to isolate the variable, we will do the same thing with the inequalities. So let's begin with our first example. 5x plus 6 is less than 76. We want to isolate our x variable. So the first thing we will do is to move the 6 over by subtracting 6 from both sides. So we're left with 5x is less than 70. And then to eliminate the 5, we will divide by 5 on both sides. And that'll leave us with x on the left-hand side is less than 70 divided by 5 is 14. So here we have our solution, and what we always want to do, we always want to make sure and check our answer. So here, when we check an inequality, you actually want to do several checks. You want to check a value that satisfies our answer. We want to choose a value of x smaller than 14 and make sure that it does indeed check, so let's do that. Let's let x equal any value smaller than 14, let's say 10. You can choose any number that you want, just so long as it's smaller than 14. And let's plug it into our inequality. So we have 5 times 10 plus 6. We want to make sure and verify that that is indeed less than 76. So 5 times 10 is 50. Plus 6, is that less than 76? Well, 56 is less than 76. So it checks. Okay. You also want to check the actual value. Let's say if you were to plug in x equals 14 back into your inequality, you should get a false statement because x needs to be strictly less than 14. Likewise, if you were to plug in a value greater than 14 back into the inequality, it shouldn't check either. Values that are smaller than 14 are the only values that should check. Okay. Let's take a look at how we want to actually write our answers. The solution can be written using 3 different notations. The first notation is the set notation. With the set notation, we have these fancy brackets here, okay? And all that means is the set of all x such that x is less than 14. So here's our x less than 14 solution that we got earlier. And then we just put brackets around it. And then we put this vertical line here. And that vertical line means such that. So if I were to read my answer, it's the set of all x such that x is less than 14. Okay? And so it's nothing more than taking your answer and putting it in braces. Then we can graph our answer, okay? The graphing notation. And here we have our number line, and all I do here is put my number 14. And what we want to do is, because x is less than 14, we want to shade our number line to the left of 14. Okay? Those are all of the x values that are smaller than 14. Now here at 14, because x is strictly less than, we will use an open circle. Okay? Because it doesn't actually include 14. The third notation we can use is called interval notation. And essentially what that is, if we were to look at our graph notation, we see that our graph, the arrow, is going to go all the way to negative infinity. And that will be the first value that we put here, negative infinity. And it's going to go up to, but not including 14. So it goes from negative infinity to 14, and we will use parentheses around that. We always use parentheses when we're talking about infinity, positive or negative. And here we'll use a parenthesis because it's not inclusive. We're using the open circle here, and it's strictly less than. Okay? And so just to review inclusive and exclusive notation, whenever your inequality is greater than or equal to, or less than or equal to, we always want to use brackets on our interval notation, or a solid point on our graphing notation. When we have an exclusive that's strictly greater than or less than, we want to use parentheses on our interval notation and an open circle when we're graphing. And the exception to that is we will always use parentheses when we talk about positive or negative infinity. So that's how you solve a linear inequality. When multiplying or dividing by a negative number, you must reverse the inequality symbol. So, for example, okay, so let's solve this inequality. We have negative 2m plus 8 is less than or equal to negative 4m. Now, unlike our first example, the variable that we're trying to solve for occurs on both sides of the inequality. Okay, so our first step will be to move one of our m's to the other side so that we can at least get the m's on one side. So I'm going to take this negative 2m and I'm going to move it to the right hand side by adding it to both sides. That'll leave me with an 8 is less than or equal to negative 4m plus 2m is a positive, negative 2m. Now, in order to isolate my m, I will divide by a negative 2. Now here is where we need to be careful. Whenever you divide or multiply by a negative number, you must reverse the inequality. So on my left-hand side, I have negative 4. But instead of less than, it is now greater than or equal to. And on my right-hand side, I have isolated my m. Okay, so since we divided by that negative 2, I had to reverse my symbol. Okay. Now, negative 4 is greater than or equal to m. That's what we got when we solved the inequality. But I'm going to rewrite this just a little bit, and it's something that you want to get in the habit of doing, and that's always putting your variable first. So instead of the negative 4 is greater than or equal to m, I'm going to write it as m is less than or equal to negative 4. Okay? Notice that the inequality is still opening up to the negative 4. We didn't change the meaning of the inequality. We just rewrote our answer a little bit, okay, to make it look nicer. Okay? And as usual, we would want to check our answer. Now this time, because it's an inclusive inequality, I can choose an m value of negative 4, and it should check. Okay? So if I plug in negative 4 into my equation, negative 2 times negative 4 plus 8 is less than or equal to negative 4 times negative 4. You plug in your m value wherever you see an m in your inequality, and then let's verify that this is a true statement. So I get a positive 8 plus 8. Is that less than or equal to a positive 16? Well, 8 plus 8 is 16. And is 16 less than or equal to 16? Well, it's not less than, but it certainly is equal to. So when m is equal to negative 4, it checks. If you were to choose a value greater than negative 4 and checked it, it wouldn't check. Okay? So again, with your inequalities, when you check them, you want to be sure and choose more than one value when you're checking. Here, I'm just checking it with one single value. Okay. Let's go ahead and write our solution using our three different notations. So our first notation, our set notation, I simply take my answer, put it in fancy braces, so it's the set of all m such that m is less than or equal to -4. Okay. There's my set notation. My second notation would be to graph, so I'll draw myself a number line here. So we'll draw in a -4, and we want m values that are less than -4, so we will shade to the left of -4 and add an arrow to the end. And because this time it's equal to, we will use a solid point. Okay, so there's our graphing notation. And then our third way to write our answer is interval notation. So looking from our graph, we see that we have negative infinity here. So all our values will go from -infinity all the way to -4. So you'll recall that we never include infinity, so we'll use a parenthesis on our infinity, and we'll use a bracket on our -4 because it is including -4. So remember that you always need to, when dividing or multiplying by a negative number on an inequality, you need to reverse the inequality symbol. So let's take a look at this next example. Now this example is a little bit more complicated than the previous examples, but the rules don't change. We would solve this the same way we would solve a regular linear equation. The first thing I'm going to do is I'm going to do some distributing. I'm going to take my 2/5 and I'm going to distribute it in to the k plus 2. And on the other side, I'm going to take my 1/4 and distribute it in to the 2k and the 6. So 2/5 times k will give me 2/5 k plus 2/5 times 2 will give me 4/5. And that's less than or equal to 3 plus 1/4 times 2k. Well, when I simplify that, I'll get 2/4, which is 1/2 k, minus 1/4 times 6 is 6/4, but when I simplify 6/4, I'll get 3/2. Okay. Then what I want to do is I want to eliminate some of my fractions here. Okay. I have 5 in the denominator on the left-hand side and a 2 in the denominator on the right-hand side. So you'll recall, to eliminate denominators, we will multiply both sides by the LCD of our denominators, and the LCD will be 10. So I'm going to multiply both sides of my inequality by 10. And when I do that, I want to be sure and distribute that 10 into everything in my inequality. Okay, so when I multiply the 10 times 2/5, the 5 will cancel and I'm left with 2. 2 times 2 is 4, so I'll have 4k plus, again, the 5 will cancel with the 10 and I'm left with 2 times 4 is 8, and that's less than or equal to. Now the 10 multiplies 3 and I'll get 30, plus the 2 will cancel with the 10 and I'm left with 5k, minus the 2 will cancel with the 10 and I'm left with 5 times 3 of 15. Okay. What's left is to combine my constants on the right hand side. So 30 minus 15 is 15 plus 5k. And again, the variable that I'm trying to solve for appears on both sides of my inequality. Let's get them to one side. I'm going to move my 4k over to the other side. And so I'm left with 8 is less than or equal to 15 plus k. And then I'm going to subtract my 15 so that I have k all by itself. So I get a negative 7 is less than or equal to k. And as I mentioned before, we always want to write a variable first. So I'm going to rearrange my answer a little bit and write k is greater than or equal to negative 7. Okay? So that's what I get after solving my inequality. Now to check it, you want to be sure and check. Let's plug in the negative 7 back into our equation. So let's let k equal negative 7, or you can choose any number greater than negative 7. So let's check it. So we have 2/5 times, plug in my negative 7, plus 2 is less than or equal, I want to check that, to 3 plus 1/4 times 2 times negative 7 minus 6. Okay. Notice that when I plug in my variable that you want to be sure and use parentheses. Okay. Following my order of operations, I'll have negative 5 less than or equal to 3 plus 1/4. Following my order of operations, I'm going to do this what's in parentheses first. So 2 times negative 7 is negative 14, minus 6 is negative 20. Here, my 5's will cancel. I'll get 2 times a negative 1, so I get a negative 2, less than or equal to 3 plus 1/4 times negative 20. Okay, the 4 will cancel, so I'm left with the negative 5. So I have negative 2 is less than or equal to negative 2. Is that true? Sure. It's not less than, but it is equal to. Okay. So k equals negative 7 checks. Okay, and again, you can choose more than one value to verify your inequalities. Now, how are we going to write our solutions? Well, we can have our set notation. So I'm just going to take my fancy braces, the set of all k such that k is greater than or equal to negative 7. There's my set notation. I can graph my solution. So I'll simply do a negative 7, and this time we want k greater than or equal to negative 7. So greater than, I will shade to the right of negative 7, and again, because it's equal to, I'll use my closed point. And finally, my interval notation. This time, my answers go from negative 7 to positive infinity. It includes negative 7, so I'll use a bracket, and I'll use a parenthesis at infinity because we always use parentheses, regardless if it's inclusive or not on the inequality. This last example, my first step will be to get rid of my denominator here. But notice that this is a double inequality. Okay? Unlike the previous examples where we had a single inequality, here we have 2 is less than or equal to negative x plus 3 divided by 3, and that's less than 4. Now the idea here is that we want to isolate our variable in the middle. We want to leave the variable alone in the middle and get rid of everything else. Okay? The first thing I'm going to do is I'm going to get rid of this denominator of 3. So I'm going to multiply the middle by 3. I'm going to multiply the right-hand side by 3 and also the left-hand side by 3. What we do in the middle, we have to do to both sides also. So now I have a 6 is less than or equal to, the 3's will cancel, negative 6 plus 3 is left in the middle, is less than 12. Now I'm trying to isolate the x in the middle here, so I'll subtract the 3 from all three parts. 6 minus 3 is 3, is less than or equal to negative x, is less than 9. The last thing I need to do is to get rid of this negative. So I'm going to divide by a negative 1 on all three parts. Now, so I get a 3 divided by negative 1, so I get negative 3. And the same rule applies because I'm dividing by a negative number. I need to switch the direction of my inequalities. I now have x by itself, and here I'll have greater than, and now negative 9. Okay. Now, so x is in the middle. You always want x in the middle when you have a double inequality. Okay. You also always want to make sure that your inequalities are facing in the same direction. Here they're both facing left. The other thing that you want to do is you always want to make sure that the smaller number is on the left and we're working towards the larger number to the right. Well, negative 9 is smaller than negative 3. So I'm going to rewrite this a little bit. Negative 9, okay, I'm not going to change the answer. All I'm doing is rewriting it, okay. The x is still in the middle. Now our inequalities are now pointing to the right, okay. And this is the proper way to write a double inequality. Okay. Now when you go to check your answer, you want to check several values, okay. You want to check a value for x that is greater than negative 9, but less than or equal to negative 3. So let's choose a value. Okay, so let's let x equal a value smaller than negative 3, but greater than negative 9. Let's say negative 5. So plugging in negative 5 into my inequality, you want to make sure that you plug it in everywhere for x, okay, and we want to check this. So I have 2 is that less than or equal to double negative, we'll get a positive 5 plus 3 divided by 3, is that less than 4? Well, we have 2 is less than or equal to 8 divided by 3 is less than 4. Okay. Is that a true statement? Well, what's 8/3? Okay, we can rewrite that as 2 2/3. Okay. Is 2 2/3 greater than or equal to 2? Yes, it's greater than. Is it less than 4? Yes. Okay, so it checks. So finally, let's write our solution. So again, we can use our set notation. We'll take our fancy braces, the set of all x such that x is greater than negative 9 and less than or equal to negative 3. We can also graph. Let me draw my number line here. So let's suppose negative 9 is somewhere over here. Negative 3 is somewhere here. We want all of the x values in between those two numbers. So here we'll shade in. We don't want to include 9, but we do want to include negative 3. So we'll have an open and closed points there. That's my graph. And my interval notation, my x values go from negative 9 to negative 3. We don't want to include 9, so we'll use a parenthesis. We do want to include negative 3, so we will use a bracket. So there are my 3 ways to write the solution. So that is solving linear inequalities with one variable. And that's it for now.